Lecture 3 covers sections within Section 2.3. At the end of today's lecture, you should be able to perform vector arithmetic. In particular, you should be able to do the dot product, i.e. the scalar product, which is the projection of one vector onto another for 2- and 3-dimensional vectors, as well as determine the angle between these vectors. You should also be able to perform addition and subtraction of vectors. And lastly, you should be able to apply the law of sines, law of cosines, to triangles that can be used to represent force vectors or physical geometry. For us to begin, let's talk about vector arithmetic, and we're going to break it down into two categories. The first category is addition and subtraction, and vector addition and subtraction is handled just as we would addition and subtraction of any other number within this course. Now, for vector multiplication, this is the process of projecting a vector onto a line or surface. And we're going to have to introduce a new mathematical operator, the dot product, also known as scalar product, for us to do this. Now, let's talk about projection. Say we have a vector f that is some angle theta above our x-axis, and we want to know how much of f exists along our x-axis. That is, we are going to project f onto our x-axis to determine f sub x. And to do this, we are going to use a dot product. Now, in this picture, we see that if we draw a dashed line from the head of f straight down to our x-axis, that the length from our point of origination, i.e. our origin, to now the x component of our point of termination, i.e. the end of that dashed line we drew from the head of our vector down to x-axis, would define f sub x. Now, the dot product is also referred to as a scalar product because its result is a scalar value, and it is a component-wise multiplication of the magnitudes of our x, y, and z terms, and then it is summed. So, say we have two arbitrary vectors, a and b. We have a dot b, and notice a dot in between these two vectors. This does not imply multiplication. This means a dot product. And this can be expressed as our vector a, which is expressed as ax, ay, and az, dotted with vector b, which is expressed as bx, by, and bz. Now in a component-wise multiplication, we're going to take ax times bx, add it to the quantity ay plus by, and then we're going to add that to the quantity az times bz. Now notice how these terms do not cross-multiply, and that our resultant is a scalar quantity. Now we're going to address directionality shortly. That is how we take into account our unit vectors that are associated with these magnitudes. Now let us look at an application of this. Consider the following vector f that starts from our origin and ends at point A. That's defined as 5, 4, 4. We want to determine f sub x via the dot product. First we have to define f. F is 5.0, 4.0, 4.0. That is, it has a magnitude of 5 in the x direction, 4 in the y direction, and 4 in the z direction. We know our result should be 5.0, but we're going to show that with our vector dot product. Next, we recognize that since we are projecting onto the x-axis, the vector that we are going to project on is I hat, the unit vector describing the x-axis. For us to execute this dot product, we are going to calculate a scalar quantity, that is the magnitude of our force vector in the x direction. So we have f sub x is equal to our force vector f dotted with our unit vector in the x direction, I hat. So you have 5.0, 4.0, 4.0 describing f dotted with 1.0, 0.0, 0.0, I hat. And in our component-wise multiplication, we have 5.0 times 1.0 plus the quantity 4.0 times 0.0 plus the quantity 4.0 times 0.0. which gives us a value of 5.0. We know this vector exists in the x direction, such that we can find f sub x is equal to f of x of I hat. That is, our force vector in the x direction is going to have a magnitude of 5.0. Now we know this problem is somewhat trivial because we already had the x component of our force vector, but it illustrates the mechanics of the dot product.